So first of all, we will configure the topology, and after that, we will discuss the basics of MPLS. So we need to configure the MPLS core. So we will use R1, R2 as the core routers, and then we have R3, R4, R5, and R6. So these 3, 4, 5, 6 are the edge routers. Then we have two customers. So I'm going to use this 7 and 8. So these two routers belongs to one customer, and after this we have 9 and 10. So these two routers belongs to another customer. So when you do your practice, you can add 7. You can add the routers from these customers with R5 and R6 as well. I'm going to connect R1 serial 1 by 0 to R2 serial 1 by 0. R1 serial 1 by 1 to R3 serial 1 by 0. R1 serial 1 by 2 to R5 serial 1 by 0. So R2 serial 1 by 1, R4 serial 1 by 0. Serial 1 by 2, R6 serial 1 by 0. R3 serial 1 by 1, R7 serial 1 by 0. R4 serial 1 by 1, R8 serial 1 by 0. Serial 1 by 2, R3, R9 serial 1 by 0, R4 serial 1 by 2, R10 serial 1 by 0. So serial 1 by 0, serial 1 by 0, serial 1 by 0, 1 by 2, 1 by 1, 1 by 0. So 1 by 0, 1 by 0, 1 by 2, 1 by 1, 1 by 0. 1 by 2, 1 by 1, 1 by 0. 1 by 2, 1 by 1, 1 by 0. So I'm going to use these boxes to separate the networks. So this is for MPLS. So we'll configure it for MPLS VPNs. So we'll use different protocols as PEC. Yep. So these devices belongs to one customer, and this is another customer. I'm going to use IP networks 192.168, or if you want to go for public IP addresses, so you can use those. So let's say we are using 200.1.1 uh, 200.1.1.12.0/24. It's 13, sorry. So 13.0/24. Then we are using 200.1.12.0/24. 200.1.15.0/24. So basically, just to separate the different network segments, I'm going to write down. So this one is service provider. This is one customer. This is the second customer. 200.1.24.0/24. 200.1.26.0/24. Then we will configure the loop backs 111, 222, 333, 444, 5566 on these routers. Or if you want to use some one major IP network to configure the loop backs, so we can use that one as well. So here in this portion, so we are using this ISP is using 200.1.37.0/24. This one is 200.1.39.0/24. 200.1.48.0/24. 200.1.104.0/24. Then we have some private networks. Let's say this company R9, they are using 192.168.1.0/24 and 192.168.9.0/24. In the same way, uh, on this site, they are using 192.168.2.0/24 and 192.168.10.0/24. So this one is R7. So they are using 192.168.1.0/24 and they are using 192.168.7.0/24. So these are the two networks in this company. So these will configure these two end user networks as the loopbacks. So then we have R8. So 192.168.2.0/24 and 192.168.8.0/24. So these are the IP networks. So here we will use EIGRP1 as the IGP. On the top of EIGRP1, we will enable MPLS. So EIGRP1 is the underlay for the for the MPLS. And on the top of MPLS, we will run MPBGP. So MPBGP and our AS is 1. So MPBGP or multi-protocol BGP 1. So these are the protocols or technology we are using in the service provider network. So this customer is using EIGRP 100 as their routing protocol. So this customer is using, let's suppose, RIP as their routing protocol. So RIP, EIGRP, so these are the PECE protocols, provider edge, customer edge protocols, and these are the this is the underlay for the MPLS. On the top of MPLS, we are going to run MPBGP. So these are the different protocols we are using in our topology. Later on in the next implementation, I will show you BGP as PECE routing protocol, and we will add IPv6 on the top of it. So let's start the configuration of these devices. So we have to open Notepad. The first device is R1 and enable global configuration mode. After that, host name is R1, interface loopback 0. So IP address is 111.255.255.255.255 and exit. We have an interface serial 1 by 0. So the IP address is 200.1.12.1 255.255.255.0. No shut and exit. Interface serial 1 by 1. So IP address is 200.1.13.1 255.255.255.0. So no shut and exit. So interface is serial 1 by 2. So IP address is 200.1.15.1 255.255.255.0. No shut and exit. The second device is R2. On R2, host name is R2. So loopback 0 becomes 222. Serial 1 by 0 is 12.2. Serial 1 by 1, so it is connected to router 4. So serial 1 by 1, it will become 24.1. Serial 1 by 2 becomes 26.1. Then we have router 3. So we'll paste the config. So R3, hostname R3. So IP address becomes 333. So serial 1 by 0 is 13.2. So we are not configuring the rest of the interfaces at this point. R4, R4, hostname R4, loopback 0 becomes 444. So serial 1 by 0 is 24.2. And we are not configuring these two interfaces, serial 1 by 1 and 1 by 2, at this point. So then we have R5, hostname R5, loopback 0555, and 15.2. No, we are not configuring MPLS on all routers. So this is our service provider network. We have to enable MPLS only on these routers. R3, R4, 5, 6, 1, 2. So this is our service provider network. So this is our customer A and customer B. So this one is service provider. So we are running MPLS in the service provider network. So this one is our customer A, and this one is customer B. So I have mentioned here in the service provider network, we are using EIGRP1. On the top of it, we will enable MPLS. So EIGRP1 is the underlay for MPLS. And then we enable MPBGP on R3, 4, 5, and 6. So these are customer routers. So that's why we are using EIGRP 100 to route traffic between the customer edge and provider edge routers. For this customer, we are using RIP. So this is our router 5. Then we have router 6. So it becomes R6, hostname R6. So loopback 0 is 666, and it will become 26.2. So after this we have R7. R7 is our customer router. So we have to configure some loop packs. So enable hostname R7. We don't have to configure this loop pack 444 at this time. Later on, when we will configure BGP as PEC routing protocol, so we will configure this loop back at that time. So interface serial 1 by 0. So serial 1 by 0 is 200.1.37.2. So this one will become 37.2. So we have to configure some loopbacks. So interface loopback 1. So IP address is 192.168.1.1, 255.255.255.0, and exit. Then we have another loopback, that is loopback 7. So interface loopback 7, and IP address becomes 7.1. So let's copy this config for R7, and we will paste it for R8. So this is our R8. So hostname becomes R8. So it will become, it has to be 48. Yes, it's 48. So we will make it 48.2. Then we need two loopbacks. One is 2 and the second one is loopback 8. Okay, let's make it loopback 2. So IP address 8.1. Then we have router 9. R9 hostname R9. Serial 1 by 0 will become 39.2. So loopback 1. So loopback 1 is 1.1. Then we have loopback 9. So 192.168.9.1. Then we will paste it for router 10. So 10. So hostname 10. Serial 1 by 0 is 104.2. Loopback is loopback 2. So 2.1. And then we have loopback 10 and 10.1. So this is the basic config for all these routers. So we haven't configured our three customer interfaces and our four customer interfaces. So we will do it when it will be required. So now I'm going to open the consoles. So first of all, we'll paste the config for R10. So we have completed our basic config. So I'm gonna just enable the EIGRP 1 on R1, 2, 3, 4, 5, and 6. So let's go to R1. We go to router EIGRP1, and then we can set EIGRP router ID 111. And after this, we have to advertise the networks 1.0.0.0. Then we have to advertise the network 200.1.12.0, 200.1.13.0, and 15.0, and exit. So now we go to router 2. On router 2, 12, 24, 26, and 2. So this is our router 2. So router EIGRP1, EIGRP router ID. So 222. Then we have to advertise the network 2.0.0.0. So network is 192.168.12.0. Then we have the network 192.168.24.0, and we have 26.0. Sorry, these are not 192.168. I'm really sorry for this. We are using 200.1 dot. Okay, so the network 200.1.12.0, 24.0, 26.0. So now we go to R3. Router EIGRP1, EIGRP router ID is 333. So network is 3.0.0.0. Network is 200.1.13.0. Router 4, router EIGRP1, EIGRP router ID is 444. So network is 4.0.0.0, and network is 200.1.24.0. Now we go to router 5. So router EIGRP1, EIGRP router ID is 555. Network is 5.0.0.0. Network is not 192, it's 200.1.15.0. Router 6. So router EIGRP1, EIGRP router ID is 666. Network is 6.0.0.0. Network is 200.1.26.0. Okay, our underlay is configured. Okay, we will do it later. So now we'll start our discussion on MPLS first. MPLS multi-protocol label switching. So first of all, we need to understand why MPLS was introduced. So let's quickly discuss the Cisco switching methods. The first one was process switching. So process switching was the first Cisco switching method. In process switching, the router performs the routing table lookup for each packet. So that switching method was called as uh, process switching. So whenever a router receives a packet, so whether it uh, if a router receives multiple packets, so whether those packets belongs to the same flow or different flow, so router must perform the routing table lookup for each packet. So that was process switching, and it was time taking switching method. To make it faster, so Cisco introduced a second switching method, which was called as fast switching. So in fast switching, so router process switch. Process switch means performs the routing table lookup. So router process switch the first packet of the flow and adds a route cache entry for the rest of the packets from the same flow. So it made the routing table lookup process efficient. So the first packet is process switch. Then for the remaining packets, router adds a route cache entry for the flow. So remaining packets are fast switched using that route cache entry. So then Cisco introduced a third switching method, so which is called as CEF, Cisco Express Forwarding. So Cisco Express Forwarding CEF is a Cisco layer 3 switching method, and is also called as topology based switching. So in this method, uh, if we enable some routing protocol, so router builds the routing table as usual. So router builds the R cache. So these both tables, routing table and R cache. So these are stored in the RAM of the router. So when we enable CEF, so router hand over these two packets to the layer 2 or L3 switching engine. So L3 switching engine process them and hand over them to layer 2. So when router process these tables using L3 switching engine, and hands over them to layer 2 as FIB, forwarding information base, and adjacency or adjacency database. So your routing table is converted to FIB, forwarding information base, and R cache is converted to adjacency database. Uh, and then it calculates the L3 switching table. By using these two tables, it calculates the L3 switching table, and L3 switching table is called as TCAM. Layer 2 switching table is called as CAM. So it is called as TCAM. So TCAM is ternary content accessible memory. So basically, let me explain you this whole process by using an example that how your router performs the layer 3 switching. So let's say this is your router or layer 3 switch. So this router and layer 3 switch is connected to a router, and let's suppose this router is connected to internet. So we can have one or more layer 2 switches, or you can just connect end users directly to the layer 3 switch. But let's suppose these are the two end hosts. So all these devices are connected to each other. So this portion, so let's say this is one network, and this one is a second network. Let's say this one is 192.168.1.0/24. Then we have 192.168.10.0/24, and here it is connected to the internet. So this router will build the routing table. In the routing table, it will add C directly connected 192.168.1.0/24, and it is directly connected on fast Ethernet 0x1 or gig 0x1. Then we have another network which is directly connected, so 192.168.10.0/24, so F0/2. Then we have, let's say we are using OSPF between this internet and this one. So it will show you OE2 000/0, and next hop is, let's say, 192.168.10.2 and reachable through fast Ethernet 0x2. So this is our routing table on this device, on this layer 3 switch. So now let's say we are using these IP addresses. Let's say this IP address is 1.10, and the MAC address of this machine is let's say A. In the same way, this device is 1.11 and MAC address is B. So this device is 1.1, which is the gateway, and MAC address C. This interface is 10.1 and MAC address is AA. So this router interface is 10.2 and MAC address is AB. So now this switch, we are just talking about this switch. This switch will build the R cache. In the R cache, it will note down 1.10 is A, 1.11 is B, and 10.2 is AB. So router knows about its own IP and MAC. I'm just putting it here for a reference. So 1.1 is C and 10.1 is AA. So this table is, we are calling it as R cache. So router knows about these two entries, and these three entries are added into the R cache. So this is your routing table, this is your R cache. So when your router will forward the traffic, or will have to forward the traffic, so it will look for the destination. So which are the destinations? So let's say if it will receive the traffic for 1.10, so then it knows that it has to send this traffic through this interface C. So now what it will do is it will make entries into the TCAN table, that if it has to send the traffic towards uh, 000/0, whatever the destination is, so it will put the source MAC AA and destination MAC AB. So it will build these the uh, the Ethernet headers to forward these packets. That if I have to send the traffic towards internet, I will use AA as the source MAC and AB as the destination MAC. In the same way, if we have to send the traffic to 192.168.1.10, then source is C, destination is A. In the same way, 192.168.1.11, so the source will be C and destination will be the B. So it will make something like this, that it will prepare the Ethernet headers, so that when it will receive a packet, let's say this route 1.10 wants to communicate with internet. So what it will does, it will put the source IP and destination IP. So let's say source IP is 1.10. So destination IP is, let's say it is some internet IP address 200.111. So now what it will does, it has to send the traffic to the gateway. So it will put Ethernet header. In this Ethernet header, it will say the destination is C and source is A. So destination is C, source is A. So when this frame is received on this device, and it has to be layer 3 switched, so what it will does, it will just remove this header. So let's say this is the header. So if the destination is internet, so it will just remove this header and swap it with another header, and in that header it will say source is AA and destination is AB. So what it is doing, it is just swapping these headers. AB, source is AA. So this header will be swapped, and this traffic will be forwarded towards the route. So now you do not need to send even a single packet towards the software portion. So all these packets are switched or hardware switched. So we have just removed the whole that software component from the communications. So this make the Cisco devices communication very efficient. So for the industry standard devices, so they were not having any such mechanism, so that they can just get rid of routing table lookup, or they avoid routing table lookup. So for just to compete safe, they developed MPLS, multi-protocol label switching. So whatever we are doing, they want to get the same functionality, and they are just using it by they're just doing it by using the labels. So how they are doing, we will discuss it now. So when we are talking about MPLS, so multi-protocol label switching. was developed to compete Ceph layer 3 switching method used by Cisco. So it was developed to compete Ceph layer 3 switching method used by Cisco. So so this method was developed for industry standard multi-vendor environments, or all other than, let's say, if uh, all other vendors they want to use some industry standard protocol, so they can use MPLS instead of Ceph. So this is actually a layer 3 switching method. Later on, MPLS, VPN, and MPLS traffic engineering was introduced. So these are the applications or services you can run on the top of the MPLS network. But basically, it was a layer 3 switching method. So when we are talking about MPLS, so MPLS uses IPv4 routing as the underlay. So now we'll discuss some MPLS terminology so that we can understand what is MPLS. So in MPLS, so in MPLS terminology, we use a term which is called as um LSR. So label switched router. Then we have another term which is called as edge LSR. So this is edge label switched router. Then we will use a term which is called as LSP, label switched path. So after LSP, we will use some more terminology. Let's say on the edge LSR we are using FIB, forwarding information base. If your devices are unable to run Ceph, so then you will be using a routing information base or routing table. We will use a protocol which is called as LDP, label distribution protocol. So when these label distribution protocol will assign the labels and exchange the labels, so then it will form a table which is called as lib, label information base. Then MPLS forwarding table, LFIB, so label forwarding information base. So these are some of the terms. So Then the main term is label. So when we are talking about label, so label is an address used for packet forwarding in the MPLS network. So that address is called as label. And then another, we will use the same term label. So label is the encapsulation used to communicate or carry the labels, carry the label in MPLS network. Encapsulation means header. So header is also MPLS, and uh, address is also MPLS. So these both terms are called as label. So first of all, let's discuss the label address. So label is a value of 20 bits. So label is a value of 20 bits. So in these 20 bits, we can have a value from 0 to, then it is 104 and 8575. So 104, 8575. So this is the range that you can use for labels. So label is any value between these two numbers, including these two numbers. So when we are talking about these labels, so first 16 labels. So first 16 labels, when we are starting from 0, so it is from 0 to 15. So these are reserved. Reserved means unusable. So these are from 0 to 15, these are reserved, these are unusable. So then we have from 16 to 104, 8575. So this is the usable range. So usable label range. So this is label address. So it means when your router will start assigning the label, the first label will be 16. So now we will discuss label, which is encapsulation or header. So it is a 4 bytes. So in these 4 bytes, first 20 bits are used to store the label. After this, we have 3 bits. These are called as experimental bits. Then we have a single bit which is called as S bit. And last 8 bits are TTL, time to live. So 4 bytes, it means the first bit is 0. The last one is 31. So 0 to 31. So the first bit, which is 0, to this last bit, which is 19. So these are first 20 bits. So these first 20 bits are used to carry the label address, which can be any value from 16 to 1048575. So after this, let's say this bit is 20 and this bit is 22. So these 3 bits, 20, 21, 22. So these 3 bits are called as experimental bits. Then we have this bit which is 23, and then from 24 to 31. So these are TT used for TTL. So this is label, which is address. These 3 bits are called as experimental bits. This bit is called as S bit, and these 8 bits are TTL, time to live. So this is your label, any 20-bit value. Then we have experimental bits. So experimental bits are used to carry the uh, quality of service marking. So let's say if you are using COS, class of service, so that COS marking is copied to experimental bits. If you are using IP precedence, which is a layer 3 marking, so that will be copied. DHCP, IP precedence, so whatever you are using, so that will be converted to experimental bits according to your configurations. But simply these 3 bits are used to carry the quality of service marking. So after this we have a single bit which is called as S bit. S bit is also called as bottom of stack. So bottom of stack is used to show whether this is the last label or there is some more labels. So we can attach up to 3 labels with one packet. We can attach up to 3 labels with one packet. So 3 labels. The first one is for LSP. The second, maybe you are using MPLS traffic engineering. The third can be if you are using MPLS VPN as well. So that's why we need to carry multiple labels. So the first can be LSP, label switch path, to carry the traffic on the MPLS network. Then the second will be for MPLS traffic engineering. The third can be for MPLS VPN. So this is just an example why we are using 3 labels. So if S bit is if S bit is 1, it means then this is the last label. This is the bottom of the stack. If it's 0, then the next header is also a label. TTL, time to live, is used to avoid loops. So if there is no path for the traffic, if there is no label for the destination, so then we have to discard the packet. So that's why TTL, time to live, is used to avoid the loops in MPLS network. So we can say that MPLS is a layer 2.5 technology. So let's say this is your IP packet. So IP packet is carrying the IP header. So on the top of IP header, we will add the MPLS label, which is 4 bytes, 32 bits, and then we will add layer 2 header. So this is MPLS, this is your Ethernet. So that's why we are saying that it is between layer 2 and layer 3. That's why we can say it as layer 2.5. Okay, so now according to our topology, I'm not considering router 4 for router 5 and 6. We will just consider first 4 routers to understand the MPLS. So we have router 3, router 1, router 2, and router 4. So these devices are connected to each other. So let's say this one is our R3. So this one is R1, R2, R4. So right now we have enabled EIGRP as the routing protocol. So let's say this one is 333. So this one is 111. I'm just writing down the loop backs. So these are the loop backs: 333, 111, 222, and 444. So we are using EIGRP1. So because of EIGRP, I'm just gonna show you the tables. So first of all, we have enabled EIGRP1. So this 333 is on loopback 0. So this interface is S1 by 0, S1 by 1, S1 by 0, S1 by 0, S1 by 1, S1 by 0. So if we have a look on our routing table, so this is our router 3. So do show IP route. So you can see this is our routing table. And if I use a command do show IPsef, so this is our FIB, forwarding information base. So we are just talking about these networks 1, 2, 3, 4. We are not talking about any other networks. So for this router, we have 111, 222, 333, 444. So we have the same networks on this one, same networks on this one, same networks on this one. So this one is reachable through serial 1 by 0. So this one is reachable through serial 1 by 0, serial 1 by 0, 1 by 0, loopback 0, serial 1 by 0. On this router, so this one is loopback 0. So this one is through serial 1 by 1, serial 1 by 0, serial 1 by 1, and serial 1 by 0. Serial 1 by 0, loopback 0, 1 by 0, 1 by 1. 1 by 0, 1 by 0, 1 by 0, loopback 0. So this is our routing table, or fib or rib, whatever you want to consider. I have shown you both tables. So I'm just going to write down, if your router is not supporting Ceph, then you will look for the routing information base. If your router supports Ceph, then you will look for the forwarding information base. So right now this is our current situation of the routing table on these routers. So 111 on router 3 reachable to serial 1 by 0, serial 1 by 0, loopback 0, serial 1 by 0. So now what we'll do is we have to enable MPLS. We have to enable MPLS on all routers in the service provider network. And on all interfaces in the service provider network, or on all the interfaces involved in communication in the service provider network. In the service provider network. So what we'll do is, first of all, let's go to router 3. On router 3, we will say MPLS IP in the global configuration mode. This command will enable MPLS on your router, like you use IPv6 unicast routing to enable IPv6 routing on your router. So this command MPLS IP will enable MPLS on your network. So now we can have two protocols, or we have to enable one of them. First protocol is TDP, Tag Distribution Protocol, which is Cisco proprietary. But we have to go with LDP, Label Distribution Protocol. So we will say MPLS label protocol. If you use question mark, it will show you both options. So default is LDP. I'm just showing you the command. So MPLS label protocol LDP. So after this, we have to tell MPLS to use loopback 0 IP as the router ID for LDP. So MPLS LDP router ID loopback 0 force. So otherwise it can take any other interface IP address as the router ID. So we have to use MPLS LDP router ID loopback 0 force. So if we have a look on our topology, we have only one interface which is participating in the communication on this router, and that interface is serial 1 by 0. So we have to enable MPLS only on this interface, serial 1 by 0. So we'll go to interface serial 1 by 0, and we will enable MPLS IP. So this command will enable MPLS IP on this interface. So this is the configuration which we have to do on all devices. Just for your reference, let's quickly paste it here. So MPLS IP, MPLS label protocol, LDP, MPLS LDP router ID, loopback 04, interface serial 1/0, MPLS IP. So now we will enable it on other routers. Then the next one is R1. On R1 we'll say MPLS IP, MPLS label protocol LDP, MPLS LDP router ID, loopback 0, ports, and then we go to interface serial 1/0, and we will say MPLS IP. We'll go to interface serial 1/1, and we'll say MPLS IP. So now you will receive a message that LDP neighbor is up. So your LDP neighbor relationship is up. So after this, we'll go to the second router, the third router, which is R2. So we'll say MPLS IP. Then we'll say MPLS label protocol LDP. Then we'll say MPLS LDP router ID loopback 0 force. And then we'll go to interface serial 1/0, and we will say MPLS IP. So then we'll go to interface serial 1/1, and we'll say MPLS IP. The last router is R4. We'll go to R4. So we'll say MPLS IP, MPLS label protocol LDP, MPLS LDP router ID loopback 0 force interface serial 1/0 and MPLS IP. So we have enabled MPLS in our end. So basically, when you use MPLS IP in the global configuration mode, it enables MPLS on your router. And then if on the physical interfaces, you want to establish the LDP neighbor relationship, you want to participate that interface in the MPLS traffic forwarding. So that's why you have to tell MPLS IP under the interface configuration mode. So we haven't tell MPLS IP on the loopbacks on any other interfaces. We are just enabled on the interfaces which are the part of the MPLS network. So let's say let me show you some others. Write down some stuff. So this router is involved in two types of traffic forwarding. So let's say this portion belongs to the MPLS traffic forwarding, and this portion is involved in the IP forwarding. When we will configure the customers, so those customers will not be used to communicate through labels. So traffic will be forwarded using the IP routing. So that's why we have to specify that we want to enable MPLS on this specific interface. In the same way, this router, so this portion is in the MPLS network, this portion is not in the MPLS network. So that's why we can say that this device is Edge LSR, an MPLS device which can participate in IP routing and label forwarding. So that device is called as Edge LSR. So this device is LSR, label switch router. So this device does not support the simple IP forwarding. So that's why we have enabled on all interfaces. Uh, in the same way, this router is also LSR. So label switch router. And this device is again Edge LSR. So the path between two Edge LSRs on which we can communicate using the labels from this point to this point. So this path is called as LSP, label switched path. So that's why, because we have enabled MPLS IP in the global configuration mode, MPLS is enabled on that router. We don't want to enable MPLS on all interfaces. That's why it is something like you advertise the networks into some routing protocol. Let's say you are using two routing protocols. Some interfaces are in the BGP and some interfaces are in OSPF. So you have to advertise, okay, this interface will participate in BGP forwarding. This will interface will involve in OSPF forwarding. Is it clear? So when we enable this, so these routers will establish the LDP neighbor relationships. It's not like that. So basically, it is a best practice that you enable in the global configuration mode and then you enable on the interfaces. So your router is involved, but let's say you configure the IPv6 address. But if you do not enable IPv6 unicast routing, so then you can use IPv6 addresses on the interfaces, but your router will not be able to perform the routing. So now these devices will establish the LDP neighbor relationship. So first of all, so LDP hello messages are forwarded or multicasted on 224.0.0.2. All routers on a subnet multicast address, and then they will use the UDP port, UDP or TCP. They can use both ports, 646. So this is the port number which is used for the LDP, label distribution protocol. Some implementations use, some purposes, for some purposes use the TCP, some implementations use the UDP. So on, so when they exchange the neighbor relation, they exchange the hello packets. So they establish the neighbor relationships. So when the neighbors are up, so now what is the purpose? Why we are gonna enable or use these neighbor relationships? Basically, LDP is used to assign the um, labels to all destinations in the routing table. So let's say we have some destinations uh, because we are just focusing on 1, 1, 2, 2, 3, 3, 4, 4, which are the loop back addresses. So first of all, let's say we have 1.1.1.1. Each router LDP will assign the labels. Label distribution protocol will assign the labels. So each router assigns the labels to all destinations in the routing table. So this is our first network, 111. Then we have 222. So then we have 333. Then we have 444. So basically, when we are talking about 111, so each router will assign a local label. So local label is 16. This is the first network in the table. So that's why basically this table is called as label information base. So each router assign the labels to all destinations in the routing table. So local label is 17. So this one is directly connected. So that's why it will not assign the label for this network. So that's why you can say it as This one is implicit null. Implicit for directly connected networks, implicit null. And then this is 444. So local label is 18. So this is the local label. So this is the second device, which is R1. So for 11111 is local, so that's why we will use implicit null label. So 222 will be 16. 333 will be assigned with the label 17, and 444 is 18. R2. So this one will become 16. So 222 is the local, so that's why implicit null, 17 and 18. R4. So 111 is 16. 222 is 17. 333 is 18. 444 is implicit null. So these are the local labels. So each router will assign a label to each destination in the routing table. And after that, they have to exchange. So these LDP neighbors exchange their labels with each other. So this router has one neighbor, which is 111. So that's why I'm just gonna put R1. So R1 label for 111 is implicit null. Implicit null means I'm just gonna write it down as um, basically, okay, let's write down implicit null. So for 111, R1's label is implicit null. For 222, R1 assigned a label 16. For 333, R1 assigned a label 17. For 444, R1 assigned the label 18. So these are the labels received from R1. On R1, we will receive the labels from R3. So for 111, R3's label is 16. R2's label is also 16. So for 222, R3 label is not L2. So basically it is between layer 2 and 3. So we are just trying to avoid the routing table lookup. So we are not mapping it with it at the frame level. So basically instead of using the IP routing table, so we'll use LFIB to forward the traffic. Ethernet header will remain there. So for 222, R3 label is 17 and R2 label is implicit null. So for 333, R3 label is implicit null and R2 label is 17. So for 444, R3 label is 18 and 18. R2 label is also 18. R1 and R4, two neighbors. So for 111, R1 label is implicit null, R4 is 16. For 222, R1 label is 17 and R4 label is also 17. For 333, so R1 is 17 and R4 is 18. For 444, R1 is 18 and this one is implicit null. So this router has only one neighbor, which is R2. So R2 label is 16. So for 222, okay. So R2 label is for 222 is implicit null. For 333, R2 label is 17. So for 444, R2 label is 18. So this is how this table is formed. So this table is called as label information base. In label information base, so each router will store the local bindings and remote bindings. So basically local labels and remote labels. So if we go to R3 and we use the command show MPLS LDP bindings, show MPLS LDP bindings. So we are just focusing on these ones. So this is your, so local binding is 16 for 111. This is R3 and then remote binding is implicit null. For 222 it is 17 and 111 16. You can match here. In the same way for 333 implicit null local, remote is 17. So local is 18, remote is also 18. So this table is called as lib. So these routers has assigned the labels exactly as we have discussed here. So if you just want to verify on any one of other routers, you can use show MPLS LDP bindings. So local implicit null for 111 and 1616. So implicit null 1616. So all these bindings are matching. So now basically we will have to look for the direction. Let's say if we want to send the traffic for 444, so in which direction we will send the traffic. So that's why we have to uh, consider the label of the next hop router. So from these tables, now we will form the LFIB, label forwarding information base. So this is the forwarding table. We call it as label forwarding information base. So this is the MPLS forwarding table. So each router will use the lib to form the LFIB. Let's say 111. So 111 local is 16, and we have to remove the label before sending it towards next hop router. So you just have to look here. So this is your 111. So local is 16, and we have to send the traffic towards R1. Implicit null means we have to pop means we have to remove the label and send the traffic without the label towards the R1. So we have to remove these LSP labels one hop before the destination. So this is called as PHP, penultimate hop popping. So the second is 222. So for 222, local binding is 17, and we have to send it by putting the label 16. So local is 17, and we have to send the traffic with label 16. Then we have 333. So 333 local label, basically it is connected on our loopback interface. So that's why we will just put, we have to send the traffic on loopback 0. So 444 local is 18, and we have to send the traffic towards the next hop router with the label 18. So this is the label swapping information. So local swap, local is 16, then we will remove the label and send the unlabeled without any label traffic towards the next hop router. Local is 17, we swap it with 16. For 333 it is connected on loopback 0. Local is 18, we have to send the traffic with 18. So in the same way, on this router, the second router, 111 is connected on loopback 0. Then we have 222, 333, and 444. So for 222, so local binding is 16, and we have to send it by removing the label pop. So for 333, the local label is 222 is 16, 333 is 17. So it is 17, and we have to remove the label before we send it towards the next hop router, which is R3 pop. So for 444, it is 18, and we have to swap it with 18. So we have to send it with 18. On this router, so 111, so local is 16, and before we send it towards the destination, we will remove it pop. So 16, 222 is connected on loopback 0. So 333, so local is 17. So when we have to send it towards the destination, we have to send it with R1s. So R1 is also 17. So R1 is 17. So R4 we will receive with 18, and we will remove the label because R4's label is implicit now. On R4 we will have 16, and we will send it with 16. So for 222, local is 17, and we will remove the label pop. So for 333 it is 18, and we will send it with 17 because R2 assigned 17. So this is connected on loopback 0. So now this table is used to forward that traffic. If we go to router 3 and we use the command show MPLS forwarding table. So now you can see for 111, so 16, and we have to pop the label before sending it to serial 1 by 0. So then for 222, 17, and we have to send it with label 16. So 17, 16. In the same way, 333 is connected on loopback 0, that's why it's not here. So 444, 18, 18. So this is the LFIB table, and here you can see the table on the router. In the same way, if we go to router 4 and we use do show MPLS forwarding table. So the first one 111 16 16, so 16 16. For 222 17 and pop, so this is your 17 and pop. For 333 18 and 17, so 18 and 17. So 444 is on loopback 0. So we have successfully configured the MPLS in the service provider network. So if you want to just verify the LSP, we can say trace 333 source 444. So now you can see your traffic is forwarded using the labels 17 17, and then it is removed. So 13.2 is received without label. So basically edge LSR. So PHP. So PHP penultimate hop popping. So each router assigns the implicit null label for the directly connected networks. And send the implicit null label to the neighbors. So when the neighbor see the implicit null label, then it removes the LSP label and send the IP packet towards the destination router. So this process is called as penultimate hop popping. So why it is required? Sometimes we are using multiple labels. As we previously discussed that we can put up to 3 labels. Let's say we are using MPLS traffic engineering, we are using LSP, we are using MPLS VPN. So LSP. So this LSP label is used to communicate over this network. Traffic engineering, let's say you have multiple paths between these two edge LSRs and you want to involve layer 4 information into your routing. So basically in MPLS traffic engineering, we use the constraint based protocols. Let's say if we are talking about OSPF in MPLS traffic engineering, we use constraint based OSPF. That constraint can be your layer 4 information. Let's say we have two paths to communicate between edge LSRs, LSR 3 and 4. So we want to use one path if the traffic is for port 80 and or port 2021. We want to use the second path if the traffic is for SMTP, POP3, or for email protocols. So in this way, we can convert the traffic between these two HLSRs in two streams. So one stream, for first stream, first path is best. For the second stream, second path is best. So that's we need an MPLS traffic engineering label so that we can communicate. But again, LSP label is required for traffic forwarding on the MPLS network. So when we receive those streams can carry the traffic for different customers. So then we need to separate the traffic for the customers. That's why we need a third label, which is MPLS VPN. So if all three labels are removed by edge LSR, if all three labels have to be removed by edge LSR, then there is a lot of overhead on the processing and memory of edge LSR. So that's why we want to offload edge LSR from removing the LSP label. So that's why for the directly connected networks, each router will assign the implicit null and send that implicit null label to the neighboring router. When this neighboring router will receive implicit null, so before the sending for the traffic for 333, it will remove the LSP label and then traffic will be forwarded to R3 with two labels if we are using all three services, all two services, traffic engineering and VPN. If we are using one service, then we will send the traffic with the one label, which is MPLS VPN label, towards the R3. So this is just a way to offload uh, from the processing of LSP label on the edge LSR. So this thing is called as penultimate hopping. So now we can see that on our network we can communicate. It is default. It's the default behavior. So trace route 44444, source 33333. So now we are communicating using the labels. We are just sending the labels. Each router is just swapping the label and forwarding the traffic towards the destination. So we have avoided the routing table lookup. So we'll keep up to here today. If you have any questions, so you can ask. So tomorrow, or not tomorrow, in the next class, we will start with MPLS VPN.